you copied it from someone, then I will tell you that you will not do well on the last exam unless you can do one of these problems cold. So you're going to either get a problem like 32 or 33 on the exam. You're going to need to do it. And that's going to typically be requiring you to solve for heat transfer coefficient for an annulus, one for an inside of pipe, a couple of different fluids, evaluating the properties, choosing the right correlation, coming up with a U value, solving for length, or something of that nature. Okay? So, be fair warned. You're going to have one of those on the last step. Okay. Josh, back to Josh. Brody. All right. Anthony. Okay. Wyatt.
Greg.
Darren.
Sit down.
All right, and Abdul and Wyatt.
Greg, please.
Timesheet. Okay, homework that's due today, I'm going to cover right now. So pay careful attention. And you should be referring to, as the homework, I believe, homework 12.1, example 12.1 in your textbook. All right, we left off with the definitions. In the last definition we talked about radiosity, and now we're moving into something else. I'm going to conclude last time's lecture, and then we're going to get into black body radiation, which is the subject for today's lecture. But before we do that, I need to talk about intensity. Intensity is given the symbol I sub E, or spectral intensity is I sub lambda E. And intensity is defined as the radiant energy rate emitted by a surface per unit area projected normal normal to a given direction per unit solid angle. That's kind of a mouthful.
Perpendicular or parallel?
Perpendicular.
Aren't there a lot of perpendiculars to a direction?
Absolutely. And that's why you have to know something about the areas. Okay? Intensity differs from emittance, for example, even though they're related. Because intensity is how much you emit that's absorbed by a particular surface. All right? So, the definition for the spectral emissivity is defined as the heat transfer divided by dA cosine of theta cosine of omega cosine, or excuse me, d omega d lambda. Cosine of theta d omega d lambda. This is equal then to a function of wavelength and the azimuthal and the direction. I'll leave it at that. So this has both directional and spectral dependence. This is equation 12. Now, we're not going to work with this equation per se, but we're going to work with the variance of this equation. Before we do that, let's address Scott's issue of directional, your directional dependence. All right. We're accustomed to dealing more in 2 dimensions, frankly, in engineering than we are in 3. And when we talk about a 2-dimensional angle, we're talking about a plane angle, and we look at a projection, something of this nature. Well, here's our angle theta, or, excuse me, this is going to be d alpha, and we'll define that as being equal to dl divided by r, where dl is the arc length, and r is the radius from the projection point to the surface. All right. Let me go back here. Intensity has units, I forgot, of watts per square meter per steradian, which is given the symbol SR, or watts per meter squared per micron per steradian, per spectral emissivity. All right, so this is what we're familiar with the plane angle. And you're familiar with, this would be our DL, our arc length, this is our radius, this is our angle alpha. Now, when we look at 3-dimensional projections, we deal with what's known as a solid angle. And that looks something like this. We project in this fashion. And this is d omega your solid angle. This is your area DAN, which is the area normal to the projection. This is your distance R to the center of the area, and that is the area normal or perpendicular to the direction. And there at d omega is your solid angle. And there are 2 pi steradians in a hemisphere. omega is equal to D, change in the area over R squared. And we're going to use, this is what you're going to use in your homework. All right. So, let's talk about the heat transfer that occurs. From equation 1210, dq, and if we do dq spectral heat transfer, dq lambda, would be equal to the spectral intensity times dA1, where 1 is the surface itself, times the cosine of theta, excuse me, this is I di, and then d omega. That's the solid angle. So the heat transfer, which is going to be emitted, the radiant energy emitted, which is going to be absorbed by some area dN, is going to be equal to the area which is emitting times the cosine of how that area sees the other surface off of its normal, times the solid angle which the two surfaces create. And the solid angle, and this equation right here is what you're going to use, except you're going to approximate it in your homework as, instead of differential, you're just going to approximate it as the heat transfer and the one area. Okay? And the omega will then be equal simply to the area of the other divided by the distance between the two. Okay? Yes?
That's your book approximated by not.
Yeah. That's exactly right. Good job. Where's Abdul? Josh? Where's Abdul?
I don't know. I can text him if you want.
Huh?
I can text him if you want.
You got his text?
I can text him.
You have his phone?
I have his number.
Yes. All right, texting. Tell the entire class. 34 plus 1 people are wondering right now where he is.
If he
All right?
doesn't show up.
And that we are talking about what's going to be on our exam number 3, as long as nobody tells anybody outside of the class that's not here right now what's on that test. All right? Tell him to enjoy sleeping in. All right. We can also redefine d omega in terms of geometry. And if we do that, we can say that d omega is equal to the sine of theta, d theta, d phi. And this is equation 12(8). This is the alternative. This comes from the equation that I wrote over there, which is equation 12(7). And the derivation of that is in your textbook. All right? I'm going to make that substitution. And if we divide out the area of the emitter, we have the spectral flux is then equal to the spectral intensity times the sine of theta times the cosine of theta times d theta d phi. And we will then integrate this twice, once from 0 to pi over 2, and once from 0 to 2 pi. This is phi, this is theta, so one is circumferential, and one is for the entire, is directional, to get the whole hemisphere in. And and if we integrate that over the entire hemisphere, what do we have? I've written it up there. We have the emissivity. Okay? So what is intensity? It's that portion of the emissivity which is received by another surface, emitted by one surface and received by the other. Okay? So depending on how we integrated this, we would be able to determine how much radiation was caused by another surface. In general, and this is the important thing, for a diffuse emitter, and that is an emitter which emits in a uniform fashion. In other words, if this sheet were a diffuse emitter, everything that it would see would receive a proportional amount of radiation. Okay, so it's not stronger in one direction or the other. For a diffuse emitter, intensity is not equal to a function of direction. And that's useful to know. In that case, the spectral emissivity is simply equal to pi times the spectral intensity. Or the total emissivity is equal to pi times the total intensity. We'll use this a little way. Alrighty. I strongly recommend that you review example 12.1. They make this assumption for small surfaces that we can just approximate this differential by using the areas, and that's how you'll solve homework 35 if you haven't already done so. Okay, so that brings us to today's class. Did I pass out the timesheet? Never can remember. All right, and today we're talking about black body radiation. Black holes, black bodies, it's not a coincidence that we use similar terminology. What do you know about a black hole?
Only radiation source?
No, no radiation.
Hawking radiation?
What?
Hawking radiation?
Well, maybe Hawking's come up with a new, yeah, I have heard something about that. I don't know if I heard that on the Big Bang Theory or actually read about it, but in any case, in general, black holes, nothing escapes. No light, no radiation. That's the normal pattern. And black bodies, we have the same philosophy. No radiation escapes. So any radiation that strikes a black body is absorbed. Okay? So it is, black body is the standard. First of all, let me say it is the standard for comparison. We're going to compare other bodies to black body performance. Okay? It is a perfect diffuse emitter and absorber. Now here's where the comparison between a black body and a black hole go away. Black bodies don't emit. Our black holes supposedly don't emit Hawking radiation notwithstanding. but black bodies do, and they are perfect emitters, and they emit diffusely, and they are perfect absorbers. So whatever hits them, they keep, and they emit in a diffuse pattern. So that means that alpha for a black body is equal to 1. Okay? So transmissivity and reflectivity are both equal to 0. All right? So in other words, a black body is perfectly opaque. Opaque meaning you can't go through or can't see. All right, you also use the terminology E sub B as being equal to black body emissive power. Okay? Our E sub lambda B as spectral black body emissive power. Now you'll see in a moment why black bodies are so useful to us. Next thing I want to talk about is Planck's law. The derivation for Planck's law is in your book on page 749. And Planck was the studied black body radiation and developed a relationship to define black body spectral or monochromatic emissive power. And that relationship is equation 1230 in your book, and it's equal to a constant C1 over the wavelength to the 5th power times E with an argument of C2, another constant, over lambda times temperature in Kelvin minus 1. And those constants are defined on page 749 for you. We're not going to go into it now because we're never going to use this equation actually. We're going to use the results of this equation. This is equation 1230. Okay? So using that, we can actually produce something which is pretty useful. And that is total emissive power. All right. If we wanted to know the total emissive power of a black body, we could integrate Planck's equation over the entire spectral universe, from 0 to infinity for wavelengths. All right? And if we do that, using this equation, we end up with a very interesting result. And it's displayed on page 751. The result of that integration is this result. And you've seen this result. We started off in the first day of class when we talked about, in your reading assignment, about how radiation is equal to this, a function of the temperature of the body to the floor. All right? And so, what we have here is black body, emissive power, is equal to the temperature of the body times sigma. What is sigma? You remember from physics? The Stefan-Boltzmann. I think that's ST-TA. And it's equal to 5.669 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. Now, Stefan-Boltzmann constant, what?
6 times.
The Stefan-Boltzmann constant is in the back of your textbook, and it's a good place to know where these are. All right, so when you're doing a test, because you're going to use this, it's on the back under physical constants, 5.67 times 10 to the minus 8 watts per meter squared Kelvin. All right, now what does that mean to us? What is the value of that to us? This is equation 1232. We wanted to know how much emissive power this sheet of paper was giving out. I could measure its temperature. Okay, clearly this is not a black body. But if somehow or another I could relate its physical material properties to that of a black body, then I could come up with a ratio where the emissive power of this sheet of paper compared to the emissive power of a black body could be related to a material property, and then I could multiply that material property, which would be less than 1, times sigma, times the temperature of the paper to the fourth, and what could I come up with? The emissive power of the piece of paper. Now, John.
Are we talking about like black bodies and like the total? Is this like kind of like the max power that a system can kind of like withhold?
That's right.
In a way?
The black body is the standard for comparison. So it is the perfect emitter, all right? So for any body at that temperature, you're not going to emit more energy than a black body emits at that temperature, okay? All right. Okay, and this is the equation coming from Planck's law, which allows us to relate that analytically, numerically. Questions? All right, so let's see how we're going to do this. Kind of giving you a hint. Now, we need to take a look at something called the emissive power. How we can determine the emissive power for this sheet of paper. Now the problem is that just like material properties for different metals and other materials change as a function of temperature, you recall that. Well, the problem is that the emissive properties of materials change as a function of what?
Spectrum.
Right, wavelength. Very good. So that complicates things quite a bit. So let's just take an example here. Let's say we had a graph, like so, and here we had the spectral black body emissive power, and this is lambda, and we had a curve that looks something like this. Okay? And I'll put this as lambda 1, and this is lambda 2. So this is, in this case, some black body, and it is emitting over a certain frequency between zero, not frequency, over a certain wavelength between 0 and lambda. And we're interested to know how much emissive power is emitted by this black body between lambda 1 and lambda 2. Okay? So that's what we want to find. What is the emissive power of a black body, the black body, shown above, between lambda 1 and lambda 2. Now, we can do that, can't we? How would we do that?
Integrate 12.3.
Right. We can integrate 1230 between lambda 1 and lambda 2. And that's exactly more or less what we're going to do. We're going to take and integrate between lambda 1 and lambda 2. To do that, though, we need to know what? We're going to need to know all of the constants and what have you. We're going to need to know this curve. But we're going to do it a little differently. Here's what we're going to do. We are going to define, now pay careful attention now, because this seems a little complicated, but it's not very complicated at all. All right, we're going to define this integral between 0 and lambda 1 of the spectral emissivity. Just going to give it a new symbol. We're going to call this E sub b, the emissive power between 0 and lambda 1. Okay? Nothing complicated there. And this would be for a black body at constant temperature. I mean, if the body's temperature is constantly changing, all bets are off. Okay? All right. Now we're going to define F between 0 and lambda 1 as the following. We're going to define this as the ratio of the integral between 0 and lambda 1 of E lambda b d lambda over the integral from 0 to infinity of E lambda b d lambda. Well, this we're going to keep for the time being. But what's in the denominator? Brandon? Anyone? What? Right, which is? Okay? So what we have defined, this is the fraction of emissive power that occurs for a black body between 0 and lambda 1 at a given temperature, okay, over the total black body emissive power. emitted by that body. Okay? Which we know to be sigma, the Stefan-Boltzmann constant, times t to the fourth. With me so far? So all we're doing is introducing these variables. All right. Then we can write the following. That the black body emissive power emitted between sigma 1 and sigma 2 is going to be equal to the black body emissive power evaluated between 0 and lambda 2, not sigma, lambda 1 and lambda 2, minus the black body emissive power emitted between 0 and lambda 1. Agreed? Well, you should agree. All right. So now we're going to divide this equation by sigma t to the fourth. All right, so we have EB lambda 1 to lambda 2 over sigma t to the fourth is going to be equal to B from 0 to lambda 2 divided by sigma t to the fourth minus EB from 0 to lambda 1 divided by sigma t to the fourth. What's this? This is this fraction. Okay? All right. Or we can say that this is now F sigma 1, lambda 1 to lambda 2 is equal to F times F 0 to lambda 2 minus F 0 to lambda 1. Okay? Now, some graduate student, not too many years ago, back 50 years or so ago, probably as a result of a PhD dissertation, came up with a table that relates these fractions as a function of wavelength and temperature. So, if you know the temperature of the black body, open your books now to page 752. The table was completed by a fellow named Dunkel in the 1950s when he was a grad student at UC Berkeley. Okay? And this saves having to fiddle with all this Planck's law equation and everything else, but it all comes from that observation. And what it is if you look at the table, you have in the first leftmost column a column that is comprised of the values of the wavelength, lambda, multiplied times the temperature. Okay? So if you know the wavelength you're dealing with, in this case lambda 1 and lambda 2, and you know the temperature of the black body, then you can multiply lambda 1 times the temperature, and then go down that column until you see that value, and you can read F from 0 to lambda 1. Is that clear?
That first column is lambda 1 times.
The first column is lambda times T. If you wanted to calculate F of 0 to lambda 1, you would multiply the temperature times lambda 1, find that value in the first leftmost column, and then read the appropriate fraction. That's how you use the table. Then, you wanted to find the value of F from 0 to lambda 2. You would then take lambda 2, multiply it by the temperature, it'd be the same temperature, of course, and you would go down the leftmost column until you found that value, and then you'd read over, and you'd read F from 0 to lambda 2. Okay, everyone with me? Yes.
So we would always be given lambda 1 or 2? Or would we ever have to decide?
I'm sure that somewhere, I hate to say always, all right? Because the moment I say that, Scott will prove me wrong. In general, that's the way we normally do it. But you could work backwards on this, I suppose, all right? And be asked to solve for lambda.
Yeah, just put the table in Excel and ask it to find a way.
And Scott will send it out, and then I'm going to have to regrade the homework. Although I can't really say anything to you because you did send me a copy. You copied me on the message. Yeah, I know. So, what is he doing? He's interpolating the values. Very, very good. Very good. All right. All right. Is there any questions on this? Because you're going to use this in your homework. It's really very simple. It really is very simple. So what do you have left? You have F, lambda 1 to lambda 2. So now you have the fraction of radiation emitted by this black body in the area between 1 and lambda 1 and lambda 2. But, what do you need to know? You're not asked to solve for that. You're asked to solve for the emissive power between those points, right? But, what do we know? We know that, okay, these values are from table 12, okay? But we know that this represents the amount of emissive power, the fraction of emissive power over the total emissive power. Or I can say that the actual emissive power that occurs between lambda 1 and lambda 2 is going to be equal to this fraction times the total, and the total emissive power is this. Oh. All right? Or these two. Does that make sense? Okay. That's the good stuff right there. All right. Now, in the remaining 5 minutes, I want to introduce another topic, and that is the emissivity, which you're also going to use tonight in your homework. You may have to read the book a little bit. Emissivity is the material property that relates how well a body emits power when compared to a black body. So it is the ratio of radiation emitted the ratio of emitted radiation by a real surface, real being non-black, to the radiation emitted by a black surface at what? What? Right, at the same temperature. And it's given in spectral terms, this ratio. It would simply be the actual emissive power of the real body divided by the same amount of emissive power from a black body at that temperature. That's your definition of emissivity. This particular one would be spectral emissivity, but same idea for total emissivity. And emissivity for a black body is equal to 1. All right. I'm going to stop here rather than trying to rush this in 2 minutes. So if you can have until Tuesday, turn in the homework I just passed out.